recursive definition, in this recursive definition of sets, we see that this is a way of defining sets. Look at this. It's a way of defining sets or a mathematical object by specifying a base case. Look at that. We're talking about the base case, and the base case entails the simplest elements of a set. And then now we have the second step where we engage ourselves through the recursive rule. And in this recursive rule, we see that we give a way in which new elements can be generated from the already defined elements. And remember, the already defined elements fall under the base case. And we told that recursive definitions are especially as useful in mathematics and computer science. I think for you guys, you're doing programming, you notice that it will be important at the right time. In particular, when dealing with sequences, sets, and structures that have a repetitive or self-similar nature. So here, of course, this is more of a repetition, but now we're putting it in context where we define a set recursively by following the following steps, specifying the smallest elements of the set, and then defining how to construct a new element from the ones already defined. And the general format of a recursive definition of a set, as you can see here, you can see we're talking about this to be the the simplest or the smallest of elements. And therefore, you can obtain these x1, x2, xn all the way in terms of the base elements or the base case. So for us to understanding, I would wish to take you through this first example, and not only the first example, we shall come across a number of them. The first one entails there is the set of natural numbers. And you notice that in this case, base case is that, well, if we consider the set of natural numbers, the first natural number that in that that in some cases and therefore that first element is exactly what falls under the base case, and that is the simplest of the elements. And there is the recursive step in that case is that whenever you have a natural number, then you notice that also if you add that natural number to 1, then you're going to have another natural number. It therefore implies that at any given time you pick any number that is a natural number other than 1, you notice that you can as well express it in terms of that natural number or rather another natural number plus 1. And even that natural number n that you have, let's say if you talk about 2, you notice that 2 is the same as 1 plus 1. If it exists in that case, and that 8, which is a natural number, is the same as 7 plus 1. And that 7 that is added to 1 to get 8, it can also be obtained by adding 6 to 1. That 6 can be obtained by adding 5 to 1. So you notice that that is the recursive, that is exactly what we call the recursive step. And as it is explained here, you see, 1 is in the set, and every time we add 1 to an existing number in the set, the result is also in the set. So the recursive step should be one that will give you elements of the same set that you're dealing with. It should not give elements that are outside that set or that do not belong to that set. Example 2, talking about the set of positive integers. The first positive integer we know, of course, is 0. Or rather, well, we have to be very careful in as far as, of course, when we're talking about positive integers, yes. But in this case, you notice that this may not even hold, because then when you talk about positive integers, then you should start with 2. So this one, by the way, you start with 2 here. This one, let me do away with that. I think it will be fair. It is important that we know that here. This is not a positive integer. So what we're referring to in this case, we're talking about, well, it should be 2. Yes, it should be 2 is in the set of even numbers, because we're talking about positive even numbers. And that being the case, therefore, the first one, the simplest of the elements is 2, and any other positive integer is obtained by another, that is like in the second one, in this case is 2 plus 2. The next one is 4 plus 2, and that goes on. And therefore, you should be able even to obtain the membership of that set. So here we have 2. Yes, every time we add 2 to an even number, then we get a positive even number. That is to a positive even number. That is to a positive even number here. So in this case, the first one that starts in that case is 2, and that goes on. And in this case, suppose you asked to, let's say, define recursively the set of all even numbers. How do we go about that? Like in that case, you're asked to define recursively the set of all even numbers. How do we go about this? You notice in this case, well, the base case in that case is 0, which is in the set of, in fact, in the set of even numbers. That is, this here 0 is the base case in as far as even numbers are concerned, right? So this one is in the set. This one is in the set of even numbers. That is the base case is in the set, and there is recursive step. The recursive step in this case is I do not know whether you can see that if n is an even number, then n plus or negative 2 is also an even number. I think you can see that, because remember in this case, the first even number here that we're talking about is 0. That is the base case. If you have 0 plus 2, then you're going to have 2. If you have minus 2, you're going to have negative 2. If you have negative 2, you minus negative 2, you're going to have negative 4. Negative 4, you minus negative 2, that is minus 4 minus is negative 6, and so on. And on the right-hand side, you find that, of course, those ones are, there is a 0 plus 2 is 2. Is that, yes, this is the recursive definition of all even numbers. You have the base case, which is 0 is in the set of even numbers. And then the recursive step in that case is that if n is an even number, then n plus or negative 2 is also an even number. And that is it. So let me hope that you can see that. Here, if n is a positive, this one should be positive even number. This one should be positive, is in the set of positive even numbers. All right, I'm correcting something here. This one should be in the set of positive. Here it should be positive, right? Positive even numbers. If n is a positive even number, then n plus 2 is is also a positive even number. But in this case, now I've given you another example, the case of that is defining the set of all integers recursively, of all even integers recursively. Then you can see that we're talking about the base case, which is 0. The recursive step in that case is n is a number, then n plus or negative 2 is also an even number. Now, here we talk about recursive definitions in formal languages. And in this case, in particular, we're talking about sets of strings. Let's see what we have here. Briefly, let me see whether there is anyone who wants to join. Okay, everyone is okay. Some fellows have raised their hands. Let me see. Somebody has raised his hand. Somebody is already. What are you asking? To share the notes? I cannot share the notes at the moment when I'm teaching you. When you're having the online notes, when you're having the online class, unless you're not seeing the screen. But if you're seeing the screen, then yeah, we have a fellow called Umulinga. You've raised your hand. Yes. Point of contact. Oh, okay. That is okay. So we have this in formal language theory. We often define a set of strings. That set of strings is language. We say that we define a set of strings recursively. And the base case involves the simplest strings. And the recursive step defines how more complex strings can be built from simpler ones. An example in this case, where we have a symbol 0 and 1, of course, that represent that is that make up the strings. And in this case, we're talking about binary. When we're talking about bi means 2. So we're talking about binary strings here. And we say that if we let S to be the set of binary strings, and those binary strings are strings composed of the symbols 0 and 1, the base case in that case is the empty string, and that empty string is represented by epsilon, and this is the string with no symbols. And we told her that yes, that empty string has no symbols. And the recursive step in this case is that if X is a string in S, then you notice that we pair it. We pair either with the symbol 0 or the symbol 1. And in this case, we have 0x and we have 1x. And these two are also in S. And you should notice that these ones can commute, and therefore X or also X0 or X1 are also in, that is in S. And if this recursive definition generates all binary strings, and you can see in this case, the empty string is epsilon, the strings of length 1. So we have different lengths. You see, we shall have the strings of length 1, strings of length 3, length 2, length 3, length 4, and so on. And you notice in this case, those ones of length 1 consists of 3, 0, 1. Strings of length 2, 0, 0, 0, 1, 1, 0, 1, 1. Of course, when we talk about strings of length 3, we have 0, 0, 1. We have 0, 1, 0. You see 1, 0, 0, or 0, 1, 1, 1, 0, 1, or 1, 1, 0. Or now we have that is 1, 1, and so on. If we have strings of length 4, yes, we could have one case of 1, 0, 0, 1, or no, 1, 0, 0, 0. Then you see 0, 1, 0, 0, and so on. So crossing over to recursive definition of a set of sequences, we hear that we can also define sets of sequences of functions recursively. And we've considered a set of all sequences of natural numbers that start at 0 and increase by 1. Here we've considered the set of natural numbers that start at 0 and increase by 1. We notice that, well, we can present this in the form of what we call an arithmetic sequence. And we let S be the set of arithmetic sequences starting at 0 and increasing by 1. The base sequence, of course, the sequence with a 0 is in S. And we notice that, yes, that is the base case. And the recursive is in this case, and tells that is the elements A1, A2, all the way to AN. And in this case, at any given time, we could have even more than this. by simply adding the nth term of that sequence by 1, or rather increasing by 1. And you will keep on increasing, you see, depending on what n is, you realize that you'll always have another set of terms that are also in that sequence. And a display of that, as you can see here, you see, we have this, the base case. Of course, if we have +1, we have 1. Then when we add 1 again, we have 2, and so on, 0, 1, 2, 3, 0, 1, 2, 3, 4, and so on. One condition for the case of recursive definition is that must be a termination condition must be met. And if you can remember, a few minutes ago, I talked about the set of natural numbers. And in talking about the set of natural numbers, even a thing I talked about, of course, the base case. In that case, we consider the base case as 1, which is a natural number. And I talked of if we have 9, yes, 9 is a natural number, and it is obtained by 8, that is from 8 plus 1. What we should have in mind is that if we take the reverse process of, let's say, a certain set of natural numbers, then it should get you to, you see, it should get you to an n. So it should apply to the case where if you're advancing, then that set of interest of natural numbers should get you to some n. And that is why we've been told here that it is important to note that recursive definitions should eventually terminate. This means that starting from the base case, or the base cases, it depends on how many they are, you must be able to generate elements of the set in a finite number of steps. And if the recursion does not lead to a finite number of cases, then the definition is invalid. Therefore, the case of recursive definition does not apply there. So you notice that in this case, there has to be an end. The recursive definition, therefore, should lead you to an end. And well, going by that, or rather more of an extension of what we're talking about, there is the termination condition is the well-founded recursion. And we told you that a key feature of recursive definitions is that they are well-founded, meaning that there is always a way to reduce the problem to smaller, simpler instances that eventually reach the base case. Like what I mentioned, 9 is the same as 8 plus 1. 8 is the same as 7 plus 1. 7 is the same as 6 plus 1. And finally, you're going to get to the point where you're saying, yes, 2 is the same as 1 plus 1, and therefore it gets you to the base case. That is it. Well, the conclusion doesn't have much that when I send those notes, you should be able to, go through those ones. More of a conclusion of what exactly, what the role of there is the recursive definition. And this leaves you with an exercise here. We have 3 exercises here. You are asked to define the set, define recursively the set of course, you define the set of odd numbers recursively. You also asked to define the set of whole strings that contain exactly 3 ones recursively. Define the set of all valid parenthesis strings recursively. And this is an exercise that you should be able to work on. And I'm looking forward to at least the fellows attempting that. That marks the recursive definition of sets. What we shall do now is maybe I'll allow some brief break, let's say around 2 minutes before getting to relations. I'd wish to define and introduce you to a number of stuff. Next.